And what I'm going to talk about as per the program this morning is moles, Avogadro, nucleons, and atomic mass units. So finally, we've reached some physics, and it's come out with a very thin red pen. Come on, Mr. Red Pen. Okay, let's go for black. Okay. Who'd like to tell me what a mole is? Arthur, do you know what a mole is? It is. Now, that's pretty weird. And you think the amount of something, it sounds very vague. Normally in physics, we're much more precise. So, what do you think? Can you expand on the amount of something? You see, you're absolutely right to say it's the amount of something. The amount of something is measured in moles. And this is because sometimes you just need to know the number of some things rather than how much mass they have or how much volume they have. You just need to know the number of them. And so we define a mole. Ian, do you know how to define a mole? It is a constant. You're absolutely right. It's the number of particles in, well, I suppose what we ought to say is what 1 mole equals. And 1 mole equals the number of particles in 12 grams of carbon-12. So there you have it. That is the definition. 1 mole is the number of particles in 12 grams of carbon-12. Now, the reason that the mole came about is because in the early days of chemistry, they didn't know how many particles there were in 12 grams of carbon-12. In fact, it was even worse than that. The mole was the number of particles in 12 grams of carbon, because they didn't know that there was other isotopes than carbon-12. So now, as we've discovered more and more, we've redefined the mole as the number of particles in 12 grams of carbon-12. Naturally occurring carbon has a small percentage of carbon-14, and as the chemists look more and more closely at the molar mass, what do we mean by molar mass? Tom Zhao, molar mass. Any idea what we mean by molar mass? Well done. Mass of 1 mole of whatever it is. Let's say substance. So the molar mass of carbon-12 is clearly 12 grams. And usually they just say 12. And you need to know that it's in grams. It's the mass of 1 mole of a substance. So you can see that this argument is kind of circular. It's kind of torturous. It's kind of, well, we don't know what's going on here, but we'll just say it's kind of carbon and it's 12 grams. And the reason that the chemist chose carbon is because carbon reacts with an awful lot of things, most notably hydrogen and oxygen. And when they first started trying to work out the periodic table, they miraculously and rather wonderfully managed to do the whole thing with ratios, because they didn't actually know how many particles, whether they were molecules or atoms, were involved in these chemical reactions. They just knew that carbon always combined in a certain ratio with oxygen, and that hydrogen and oxygen combined in a certain ratio. And they gradually worked it out. I mean, we all know nowadays, for instance, that it's H2O. But of course, mass-wise, which you can actually measure, the hydrogen, despite the fact there are two of them, is a lot lighter than the oxygen. So there was quite a puzzle to work out here. And just the fact that they worked it out a long time ago doesn't make it any the less miraculous that they managed to do it. Yeah. Well, that is the point. Is that Jude? That is the point, is that actually they didn't know what Avogadro's number was. They didn't know what it was, so they just had to do it by ratios all the time. And it's only later on that we've managed to work out what Avogadro's number is. It actually proved very challenging to measure it. There's all sorts of ways that people tried to measure it. One of the ways, rather curiously, was by floating a layer of petrol on water. So they'd get a drop of petrol, and they figured that when petrol spreads out on water, by the time you've finished, it's just one molecule thick. So in that way, they estimated how many molecules were in one drop of petrol. And then that was leading on to an attempt to find out what Avogadro's number might be. They literally had no idea. It might have been 10, you know. Well, it was just a guess. I mean, obviously it couldn't be half a molecule thick. So it put a kind of upper or lower limit on it. Which way would it be? It just it gave a ballpark figure. So this is the nature of real scientific research. Now, of course, nowadays we do know what Avogadro's number is, and here it comes. It is. I'm just going to put 6. I think it's 6.0, but I forget the numbers after that. Maybe there's a 3. And it's just a number. Now, I'm going to change color at this point because, as far as I'm concerned, we don't need or want Avogadro's number in physics. We don't need or want the concept of a mole either. Because nowadays we know what the mass of a neutron and a proton is. So we tend to get all this stuff about Avogadro's number from the chemists, and boys feel very comfortable with it. But personally, I just go, yuck. It served its purpose, and I'm sorry, Avogadro, great idea to have this number, but what use is it? This kind of it's an artificial construct, a mole. It's an arbitrary number. It served its purpose, but actually, we've kind of moved on from there. So this is the way I would go about it in physics. In physics, my pen's a bit thin. Hang on. In physics, we tend to, shall we say, engage with individual particles. We know that, for instance, the mass of a proton is approximately equal to the mass of a neutron. I mean, if you write enough significant figures, that I better put approximately equal to, because they're not exactly the same, but they are exactly the same to 3 significant figures. And there it is. The mass of a proton equals the mass of a neutron, and this, therefore, we refer to as the mass of one nucleon. A nucleon being a proton or a neutron, a nucleon being something that's in the nucleus. Now this number appears in your data sheet at the front of your exam. It's a number that I remember. It's a number that I feel is much more useful than Avogadro's number. Avogadro's number takes you from reality into an artificial construct called the mole, whereas this is rooted in reality. The mass of a proton is approximately equal to the mass of a neutron, to 3 significant figures at least, and it's equal to 1.67 times 10 to the minus 27 kilograms. So that's the mass of one nucleon, and therefore we're fit to go. Now, what we need to know is, or what we need to do, I should say, so let's have another color while we're at it. An example will serve my purpose well, and I'm hoping to rely on you guys for a calculator. Here comes my example. I've got 1 kilogram of uranium-238, half-life 5 times 10 to the 9 years. What's its activity? Have you got the idea? We've got a kilogram of pure uranium-238. Its half-life is some billions of years. What kind of activity would we expect from that? How many decays per second? Would a kilogram of uranium-238 kind of roast us alive with alpha particles, or is it emitting 1 particle a day, or what? I honestly have no clue. So how do we go about finding out? Well, we know that we've got a formula that the activity equals minus lambda n. Casper, can you remind me what these letters stand for? Are you there, Casper? What about Alex? Alex, can you remind me what these letters stand for? It's not, in fact. No. This is nuclear physics. No. I better write it out in words then. Here it comes. So the moment I write up something and you're not clear what it means, then you must. It is. Because that's what we're hoping to look at here. It's the decay constant. The activity is the decay constant times the number of nuclei present. By the way, Alex, have you got your presentation ready? Because I'm hoping to get through this in the next 5 minutes, then it's over to you. Okay, so the activity is related to the number of nuclei present. So we looked at this last term. It wasn't in the exam, but the ratio is the constant is lambda, the decay constant. And if you remember rightly, the activity is dN by dt is minus lambda n. And we solved this, and we got n equals n naught e to the minus lambda t. And therefore, you can differentiate this, and we get a equals a naught e to the minus lambda t. And these two formulae describe the exponential decay of the uranium-238. But the first thing we need to do is to find the decay constant from the half-life. And we are going to use the top formula, which relates the activity directly to the number of nuclei present. So if we can find lambda, and we can find n, then we can find the activity. Okay, so here we go. We're going to change color again. Lambda. Lambda is ln 2 over t a half. We proved that last term. So it's ln 2 over 5 times 10 to the 9 years. And so we need, Chidi, have you got a calculator handy? Could you calculate ln 2 over 5 times 10 to the 9? 1 times 10 to the minus 10. And what are the units, Chidi? You're absolutely right, my son. Well done. Yes, to the minus 1. Okay, and then we need to know n. So this is the bit where I really wanted to get to. Some of you, when you were doing this toy time last term, you immediately said, oh, well, the molar mass is 238. And the next thing you did was you used Avogadro's constant, and what you didn't get right was it's 238 grams. You put that it was 238 kilograms. But I'm not going to get involved in that at all. I'm going to say to myself, okay, we've got 1 kilogram, and I want to know how many uranium-238 nuclei there are in that kilogram. So I'm going to divide by the mass of 1 nucleus. Well, there's 238 nucleons, and each one, as it says above, has got a mass of 1.6 times 10 to the minus 27 kilograms. So that's the way I would go about it. I haven't mentioned anything to do with moles. I've just said, look, there are 238 nucleons in uranium-238. That's what the number means. Yes, it's known as the mass number. Yes, it's the total number of protons and neutrons. But what it tells us is the mass of one nucleus is 238 times 1.67 times 10 to the minus 27. Avogadro, phooey. Chidi, you've got your calculator there. Tell me how many nuclei we've got. N is the number of nuclei. Okay, so that's just a number, so no unit. Okay, well, I'll break a habit of a lifetime. This is about 4 moles. And each mole is 238 grams, so 4 of them is about a kilogram. So it does work. But I just think, we're physicists, we don't need this business of moles. Okay, so now, therefore, the activity, as it says above, equals, we don't worry about the minus sign because that just tells us it's decay rather than exponential growth, is lambda, which is 1.4 times 10 to the minus 10 per year. And then n, which is 2.5 times 10 to the 24. Chidi, you're on calculator on duty. Okay, so that's the activity per year. So what are we going to do, Chidi, to convert that into becquerels, which is the activity per second? Yes, so that's per day. And then to get per hour, and to get per minute, and to get per second. Well done. So your calculator duty, well done. You're doing very well. Is Casper back, by the way? Are you there, Casper? We missed you earlier. Good, man. Yeah, I can hear you. You're a bit breaking up. Okay, Chitty, have you got an answer? 11 times 10 to the 6. So I just put that per second, first of all, so that the amazing thing about it, this is 11 mega becquerels, and yes, it would fry you. Of course, the alpha particles, so if you stand half a meter away, you're going to be okay. But a kilogram of uranium-238, pure, of course. So if you went to a uranium mine, as we heard earlier from Casper, it wouldn't be pure uranium-238, let alone U-235. But if you did get a kilogram of uranium-238, then it would be belching out 11 million alpha particles every second.